Warm greetings and good morning, dear students and friends. Today I am going to cover the course on solid mechanics or strength of materials in the topic of strain energy. You know that the strain energy is the amount of energy stored when the work is done on any body or a beam or any structural member. So in the case of axial loaded member, so what will be the strain energy stored? And in the case of a beam, so with the external loading, either it is a constant load or a uniformly distributed load or uniformly varying load, what about the amount of strain energy stored? So before that, I am defining the strain energy stored in a body. You know that strain energy is defined as the product of the deflection and the average of the load applied on the body. So it is strain energy is denoted by the notation U. So strain energy U is equal to half into W into delta, where capital W is the amount of load applied and delta is the amount of deformation or deflection of a material or a body. The unit of strain energy used is used in the case of a beam or any body is kilonewton meter or newton millimeter, or you can express in terms of joules. So you can know that 1 joule is equal to 1 newton meter. So from that you can able to convert either in terms of kilonewton meter or newton millimeter. So 1 joule is equal to 1 newton meter, that is equal to 1000 newton millimeter. Now I am going to give the equation for a material which is of a longitudinal length L and of cross-section area capital A, and of the Young's modulus of the material is capital U, and it is subject to an axial load W, capital W. So for this axial loaded material, the strain energy capital U is equal to W square into L divided by 2AE, where W is the apply load, so L is the length of the material and A is the cross-sectional area. It may be of a rectangular, square, or a circular or a hollow circular body. And E is the Young's modulus of the material, that is measured in terms of kilonewton per square meter or megapascal. You know that 1 megapascal is equal to 1 newton per square millimeter. Or if you want to go for a number of lengths, if a longitudinal body or an axial body is having a different length L1, L2 and L3 and total length is L. So where capital L is equal to a length of different position of the body, that is L1 plus L2 plus L3 up to Ln. So in that case, the strain energy stored can be defined as the capital U is equal to the integral of 0 to x W square into dx divided by 2AE. Even the Young's modulus may be varying from different section to section. You can put it as E suffix 1, E suffix 2 and E suffix 3. And you can put the lower limit as 0 and upper limit as x is equal to L. For a different length you can put it, and after that you can give for the total length of the material what is the strain energy stored. And what will be the strain energy stored in the case of a beam which is subject to an external loading? Due to the external loading on the beam, the moment produced at any section, if you want to find for the middle section or 1/4 of the span or the 3/4 of the of the beam section. So the strain energy stored capital U is equal to integral of 0 to x into m square into dx divided by 2EI. So in the case of the beam, the moment of the couple can be determined after calculating the reactions from the support condition of the beam. Then you can find the moment at any section, which is denoted by capital M suffix x in terms of kilonewton meter or Newton meter, or you can put in Newton millimeter. So in that case, here L is the total length of the beam, and Young's modulus may be varying from various cross sections of the beam to beam. But here I am taking the total length as capital L, and the Young's modulus will be the same for all different sections. It may be subject to a constant load, or it may be subject to UDL or uniformly varying load. So we can get the final work done, or the energy stored. Capital U is equal to integral of 0 to x m square into dx divided by 2ei. You know that E is the Young's modulus of the material expressed in kilonewton per square meter or Newton per square millimeter, or you can put in terms of Newton per square millimeter, that is of a megapascal MPa. And I is the moment of inertia of the beam section about the point where you are going to find the moment. So if the moment of inertia can be calculated for a rectangular, square, or a circular, hollow circular, as well as the I section or any girded section of the beam. So from that equation, you can find this total energy stored. Capital U is equal to integral of 0 to x, that is 0 to L, m square dx divided by 2ei. So these are the equations we use to find the strain energy stored in the case of axial loaded member, as well as for the beam section, which may be of any type of beams, either rectangular, cantilever, or proper cantilever, or a continuous beam. So in the next class, we are going to see about the numerical problem, actually, which is measured in terms of practical value. Uh, so thank you very much for patiently listening, and thank you for taking this strain energy stored for axial loaded member, and as well as for the beam, which is subject to any type of loading, combined loading also it is possible. Thank you very much for patiently listening. Goodbye. We can see in the next video channel. Thank you.